Our universe is a vast and mysterious place filled with wonders that never cease to amaze us. From the smallest atoms to the largest galaxies, the cosmos is in a constant state of flux and motion. Imagine a powerful microscope zooming in on a single atom, revealing protons, neutrons, and electrons. Now, zoom out with a telescope to see our solar system as one of billions in the Milky Way, which is just one of billions of galaxies. Just like atoms are made up of smaller particles, galaxies are made up of billions of stars, gas, dust, and dark matter, held together by gravity. Despite differences, there are striking similarities between atoms and galaxies. Electrons orbit nuclei, stars orbit galactic centers, suggesting deep underlying principles governing matter and energy at all scales. Atoms and galaxies, though vastly different in scale, share a similar architecture. Atoms have a dense nucleus with orbiting electrons, while galaxies have a central bulge with swirling stars, gas, and dust. This resemblance hints at a fundamental principle at play in both the microcosm and the macrocosm. In atoms, the electromagnetic force binds electrons to the nucleus. On a cosmic scale, gravity binds stars to galaxies. These forces, though different in strength, both play crucial roles in the structure and behavior of their respective systems. The mathematical equations describing forces in atoms and galaxies show intriguing similarities. Coulomb's law for electromagnetic force and Newton's law of universal gravitation both follow an inverse square law. These shared frameworks hint at a deeper connection between gravity and electromagnetism. Atoms and galaxies both exhibit dynamic processes. Electrons transition between energy levels, while stars undergo life cycles, influencing future star formation. Galaxies interact and merge, echoing atomic collisions and energy exchanges. Hydrogen, the simplest element, played a pivotal role in the formation of the first stars and galaxies. After the Big Bang, hydrogen atoms formed, leading to the emergence of the first stars and galaxies. Studying these primordial galaxies offers clues about the processes that govern galaxy formation and evolution. Rydberg atoms with highly excited electrons resemble galaxies with extended streams of gas and stars. These galactic structures, remnants of interactions or mergers, provide insights into galaxy evolution. Just as Rydberg atoms reveal atomic behavior in extreme environments, these galaxies expand our understanding of cosmic dynamics. Cesium atoms, with their magnetic properties, help us measure magnetic fields precisely. Similarly, dark matter, though invisible, reveals its presence through gravitational effects on visible matter. Dark matter halos play a crucial role in galaxy formation, much like cesium's magnetic properties help us understand atomic behavior. Francium, a heavy element, is synthesized in stars and scattered during supernova explosions. Elliptical galaxies, often formed through mergers, lack the swirling arms of spiral galaxies. These chaotic mergers trigger star formation, enriching the universe with heavy elements like francium, contributing to cosmic evolution. Our exploration of the atom-galaxy connection reveals striking similarities, suggesting a deep unity in the universe. Could there be a hidden harmony resonating across the cosmos? The universe might dance to a symphony of frequencies, a cosmic rhythm. Harmony and resonance have fascinated thinkers for centuries. From the music of the spheres to modern wave theory, the idea of fundamental frequencies persists. The universe might exhibit its own resonant frequencies influencing matter and energy. Electrons exist in a superposition of states described by wave functions. These wave functions exhibit wave-like properties with specific frequencies. Electrons emit or absorb photons at specific frequencies during transitions. This gives rise to spectral lines, identifying the composition of stars and galaxies. Nikola Tesla, the brilliant inventor, believed the universe was a symphony of vibrations. He famously stated, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." Tesla's fascination with the numbers 3, 6, and 9 has sparked numerous interpretations and speculations. His emphasis on frequency and resonance continues to inspire exploration into the interconnectedness of phenomena. The concept of harmonic frequencies, multiples of a fundamental frequency, finds expression in both the quantum world and the vast expanse of the cosmos. In music, harmonics enrich the sound of a note, creating overtones that add depth and complexity. Similarly, in the universe, harmonic frequencies might play a role in shaping the structure and evolution of matter and energy. At the atomic level, the frequencies of electron transitions between energy levels are not random. They follow specific mathematical relationships, dictated by the laws of quantum mechanics. These frequencies can be expressed as multiples of a fundamental frequency, creating a harmonic series that characterizes the atom's spectral lines. On the cosmic scale, galaxies exhibit their own set of frequencies, associated with the rotation of stars around the galactic center and the oscillations of gas and dust within the galactic disk. These frequencies, influenced by the distribution of mass within the galaxy, can also exhibit harmonic relationships, creating patterns of resonance that influence the galaxy's structure and evolution. For example, the spiral arms of some galaxies are thought to be density waves, patterns of enhanced star formation that propagate through the galactic disk. These density waves, influenced by the gravitational interactions of stars and gas, can resonate at specific frequencies, creating the majestic spiral patterns we observe in galaxies like our own Milky Way. Resonance, where systems oscillate with increased amplitude at natural frequencies, enables efficient energy transfer across scales. A vibrating tuning fork can cause a nearby fork to vibrate sympathetically. At the atomic level, resonance is crucial in chemical reactions. Molecules must collide with sufficient energy to react. Not all collisions result in a reaction. Only specific vibrational frequencies lead to efficient energy transfer and chemical transformation. On the cosmic scale, resonance might influence large-scale structures. The early universe was not perfectly uniform. Tiny quantum fluctuations created density variations. These fluctuations grew, forming galaxies and clusters. Resonant interactions might have shaped the cosmic web. Our journey into the atom-galaxy connection takes us deeper into the realm of spin, a fundamental property of particles that adds another layer of intrigue to the cosmic dance. Imagine a tiny spinning top, ceaselessly rotating around its axis. This simple image, while not entirely accurate in the quantum world, provides a starting point for understanding the concept of spin. In the quantum realm, particles like electrons possess an intrinsic angular momentum, an inherent spin that is not related to any physical rotation in space. This spin, quantized and measured in units of Planck's constant, h-bar, comes in discrete values, typically +1/2 or -1/2 for electrons, often visualized as spin up or spin down. This spin, though seemingly abstract, has profound consequences for the behavior of atoms, and surprisingly, for the dynamics of galaxies. Just as a spinning top interacts differently with its surroundings than a stationary one, the spin of particles influences their interactions with other particles and fields. In atoms, the spin of electrons plays a crucial role in determining their arrangement within energy levels. The Pauli exclusion principle, a fundamental rule in quantum mechanics, dictates that no two electrons in an atom can occupy the same quantum state, which includes their spin. This principle, arising from the indistinguishability of identical particles, shapes the electronic structure of atoms and, consequently, their chemical properties. The spin of electrons, coupled with their charge, gives rise to a magnetic dipole moment, making each electron behave like a tiny magnet with north and south poles. Imagine these tiny magnets scattered throughout an atom, their magnetic moments interacting with each other and with any external magnetic fields. This interplay of magnetic moments arising from the spin and orbital motion of electrons determines the magnetic properties of materials. Some materials, like iron, exhibit strong magnetic properties due to the alignment of electron spins within their atoms, creating a net magnetic field that extends beyond the material itself. Remarkably, magnetic fields are not confined to the microscopic world of atoms. They extend across the vast expanse of space, shaping the dynamics of galaxies and influencing the evolution of the cosmos. Galaxies, like our own Milky Way, possess magnetic fields that permeate their spiral arms, interstellar gas, and surrounding halos. These galactic magnetic fields, though much weaker than those found in atoms, play a crucial role in star formation, cosmic ray propagation, and the overall structure and evolution of galaxies. While the exact origin and evolution of galactic magnetic fields remain active areas of research, the spin of particles, amplified across vast scales, is thought to play a fundamental role. The dance of spin and magnetism shapes atoms and galaxies, transferring energy throughout the cosmos. Spinning particles exchange energy with their surroundings. Photons interact with electrons, causing energy transitions. This process is governed by quantum mechanics. On a cosmic scale, energy transfer is dramatic. Supernovae release vast energy, shaping galaxies. Pulsars emit radiation beams, powered by rotation. The universe's interconnectedness spans from atoms to galaxies. Our exploration of the atom-galaxy connection has taken us from familiar atoms like hydrogen to more exotic realms, where the properties of matter and energy become even more intertwined. Now, we venture into the realm of exotic atoms, where familiar particles are replaced with their heavier counterparts, offering new insights into the fundamental forces at play. Consider the muon, a particle often described as a heavy electron. Similar in properties to the electron but about 200 times more massive, the muon can also bind to atomic nuclei, forming muonic atoms. These exotic atoms, though short-lived, exhibit unique properties that distinguish them from their more common counterparts. Due to its greater mass, the muon orbits much closer to the nucleus than an electron in a corresponding energy level. This closer proximity amplifies the effects of the electromagnetic force, leading to stronger binding energies and smaller atomic radii. Muonic atoms therefore serve as sensitive probes of nuclear structure and the fundamental interactions between particles. In the vast cosmic tapestry, astronomers have observed structures that exhibit a similar tight embrace of matter, cold-flow galaxies. Unlike typical galaxies where star formation is often concentrated in spiral arms or central regions, cold-flow galaxies are characterized by a continuous inflow of cold gas from the surrounding intergalactic medium, fueling star formation throughout the galaxy. Our exploration of exotic atoms takes us deeper into the realm of antimatter, a mirror image of ordinary matter with opposite charges, but otherwise identical properties. While antimatter is rare in the observable universe, its existence has profound implications for our understanding of the fundamental laws of physics. Consider positronium, an exotic atom consisting of an electron and its antiparticle, the positron, bound together in a short-lived dance. Positronium, though ephemeral, exhibits unique properties that make it a valuable tool for studying fundamental physics. Since the electron and positron have opposite charges, they attract each other electromagnetically, orbiting their common center of mass. However, this dance is short-lived, as the matter-antimatter pair eventually annihilates, converting their mass into energy in the form of gamma rays. The annihilation of positronium has intriguing parallels in the cosmos, particularly in the study of dark matter. While the nature of dark matter remains one of the greatest mysteries in modern physics, some theories propose that dark matter particles could be their own antiparticles. Our journey through the atom-galaxy connection has taken us from the familiar three dimensions of space to the intriguing possibility of hidden dimensions beyond our perception. Just as a shadow can hint at the shape of a three-dimensional object, so too might the behavior of matter and energy in our observable universe reveal the influence of higher dimensions. String theory, a leading candidate for a unified theory of physics, proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. These strings, vibrating at different frequencies, give rise to the different particles and forces we observe in nature. One of the intriguing predictions of string theory is the existence of extra-spatial dimensions beyond the familiar three. These extra dimensions, curled up at incredibly small scales, might not be directly observable, but their presence could have subtle effects on the behavior of gravity and other fundamental forces. The idea of higher dimensions, though seemingly abstract, has profound implications for our understanding of the universe. Just as a two-dimensional being living on a flat surface might not perceive the third dimension, we might be limited in our perception of the true nature of reality. We began our journey into the atom-galaxy connection with a sense of wonder. We delved into atoms where electrons dance around nuclei governed by quantum mechanics. We then shifted to the cosmic tapestry where galaxies spiral and collide. Throughout, we found a profound sense of unity and interconnectedness. Despite vast differences in scale, echoes of similarity in the laws governing their behavior. We explored the concept of resonance, that intriguing phenomenon where systems oscillate with increased amplitude when driven at their natural frequencies. Could it be that the universe itself, from its smallest constituents to its largest structures, vibrates with a symphony of frequencies, a cosmic rhythm that echoes across space and time? Nikola Tesla, the visionary inventor, believed that the universe was a symphony of vibrations, and that by understanding these vibrations, we could unlock profound secrets. While his specific numerical insights remain a subject of debate, his emphasis on the importance of frequency and resonance continues to inspire exploration into the interconnectedness of seemingly disparate phenomena. The spin of particles, a fundamental property in the quantum world, emerged as a key player in the cosmic ballet. From the magnetic moments of electrons shaping the properties of atoms, to the vast magnetic fields that thread through galaxies, spin influences the structure and evolution of the universe on scales both large and small. We ventured even further, into the realm of exotic atoms, and the mind-boggling possibility of higher dimensions. Muonic atoms, with their heavier muons replacing electrons, provided a glimpse into the extreme conditions where matter interacts more strongly. Positronium, that ephemeral dance of matter and antimatter, hinted at the fundamental symmetry underlying the universe's existence. The atom-galaxy connection beckons us to explore the universe with awe and wonder. We are part of something grander, where the small and large are linked. Unraveling the universe's mysteries blurs the microcosm and macrocosm, revealing a deeper reality. The laws of physics may converge into a single elegant framework, a theory of everything explaining the cosmos. Our quest to understand the universe is a testament to human curiosity.